Previously, I posted two videos on developing the concert model. I'd like to add an epilogue. First of all, we're going to talk about what was wrong with the analysis that was done in the first two videos. We must keep in mind every model has an error. We may not know about it, but it does exist, and we always need to be on the lookout for it. The second subject I want to talk about is why we use the triangular distribution. And the third topic is how we might use some surveys to estimate parameters rather than just going to subject matter experts. So we'll talk about these three topics, and let's start with what was wrong with the analysis. Here is the concert model that we used in the last video. We determined that the cost per ticket should be set at $34.75 to maximize our profit. However, let's go look at this profit equation. Is it right? Did you see this earlier? You can see that it's actually the sum of the revenue minus the fixed costs. It excluded the variable costs. So let's fix that. We'll change this to a sum command of the three previous cells. Now our profit is $78,562. SIPmath has automatically recalculated our distribution, and we see that down here. The expected value is now $79,839, where previously it was $113,129. In this model, I have already adjusted our original distribution, our reference profit, when we did not have a probabilistic demand curve, to use the right equation, and that's reflected by this orange line. And now our new profit is the blue line. The other analysis we might want to do is to re-optimize our model now to see is $34.75 the right answer. So let's go back to Solver. And we'll just double check what we're optimizing here. So we are maximizing D41, which is the profit, by changing D6, which is our decision or our cost per ticket. That sounds good. So let's solve. We have an answer, and the answer is $39.77. It's also shown down here. So let's copy this result over to our other results. So the $34.75 was our maximum, our ticket price to maximize profit with the incorrect profit calculation, and now we've increased it to $39.77. Does that make sense? We've incurred additional costs, and to recover those additional costs we have to have a higher ticket price. We can compare our original profit distribution now to our maximized profit distribution at $39.77. So what we can see is we have much less downside, but we also have much less upside. And although I don't see the expected value here, the expected value has gone down a little bit, probably in that neighborhood of $10,000 or less. Okay, let's move on to the second topic, which was why was the triangular distribution used in the model? In our model, we use the triangular distribution for a number of elements. First of all, the attendees that were going to participate, or the tickets sold, if you will, and we identified that as the min, most likely, and max. We also use this same distribution, triangular distribution, for the fixed costs and variable costs. So what is this triangular distribution? This slide shows several different images of the triangular distribution taken from Bing Images. I'm sorry to say that several of the images are not correct. In this particular one, it identifies the triangular distribution as having an optimistic, a pessimistic, and then an expected value. And then it shows this purple line here as being the mean. But the mean and the expected value are typically terms used for the same thing, so it's a little disconcerting. Down here, we have a triangular distribution identified with a minimum, a maximum, and a mean. So here the mean was over here, and here the mean is defined here, and I'll say this is just flat wrong. Over here is another picture referring to the minimum and the maximum, and then shows the mode being the highest point of this triangle. And I agree that that is the mode, but it is a red word, if you will, in Sam Savage's terminology. We want to stay away from these purely statistical terms and use things that are more familiar to people. And so we might use the term most likely. So in our model we use the terms minimum, most likely, and maximum. Let's look at a cartoon of the triangular distribution, and let me explain it to you. So we have the value of some random variable down here in the x, and the frequency. How often does that happen on the y-axis? We have a minimum value, a maximum value, and a most likely value, or it could be the mode if you're happy with that term. And it's a straight line here and a straight line here between those points. Now the P50, that point which is there's a 50% chance of it being more or less than that number, is represented by some point in this triangular distribution where the area over here is equal to the area over here. The area on the left side of the green line is equal to the area on the right side of the green line. That's the P50. And as we saw previously in the diagram, the mean was being defined as the min, most likely, and max divided by 3. One of the advantages of using SIPmath is I don't have to take that as a given. I can actually test whether that's the right answer. So let's go do that using a simple SIPmath model. Here is a simple triangular distribution using SIPmath. We've defined our triangular distribution as having a minimum of 0, most likely of 50, and a maximum of 100. You'll notice that it's perfectly symmetrical. We can see the distribution is a histogram here, and we can see the cumulative distribution function shown over here. This chart also shows the P50 and the expected value. We don't see the P50 because it's equal to the expected value. When this is symmetrical, they're one and the same. So what if we made it asymmetric? In other words, not symmetric. So let's change this to 75. So now on the downside we go down 50, and on the upside we only go up 25. We can see the distribution of the triangular has changed. It's now not symmetric. And we can also see that the P50 here, P50 right there, and the expected value are different numbers. In this case, the expected value is less than the P50. What if I increase this to 200? Now the triangular distribution is skewed the other way. It's more to the high side than the low side. As a consequence, our expected value now is above the P50, this being the P50, and here is the expected value. And we can test that equation, whether the min plus the most likely plus the max divided by 3 equals the expected value. And we can see that this says 83.33, and I've actually calculated it here based on these numbers. And then this number here is being calculated based on the simulation that we just did. And they are the same. So hopefully that answers what is the triangular distribution. Let me add one more point about the triangular distribution. In this model, I am modeling a normal distribution with a mean of 5 and a standard deviation of 2. And I'm also modeling a triangular distribution with a most likely equal to my mean, a maximum equal to 2.5 times the standard deviation, and a minimum equal to the mean less 2.5 times the standard deviation. How do those two distributions compare? They are shown down here in our S-curve. And you can see that the normal distribution, shown in blue, is very, very similar to the triangular distributions, which I've done two different ways here, shown in the orange and the dashed black line. One of the differences is that the normal distribution goes to positive infinity and to negative infinity, and we've constrained our triangular distribution to 0 and 10. So if you are a fan of normal distributions but don't really want those tails, you can easily model them using a triangular distribution, setting the most likely equal to the mean and the min and the max equal to 2.5 times the standard deviation. We have talked about what was wrong with the analysis and why the triangular distribution was used. Let's go on to our third topic of how to use surveys to estimate parameters. In this model, I've assumed that we've designed a survey that we can give to a number of people, and it would ask them to identify what is the highest price they'd be willing to pay for this concert ticket. And we've given them a range of $25, $30, $35, so on, up to $60 per ticket. And let's assume the survey was given to 100 people, and they came back with these many responses. So there were 10 people that said they'd be willing to pay 25, 17 people would be willing to pay 30, only 3 people are willing to pay 60. Now the total number of tickets to be sold would be the cumulative. So at $25, everybody would buy a ticket. So that's 100 people. At $30, only 90 people would buy it. And at 35, 73, and so on until I get to $60, and then only 3 people would purchase it. Now what I want to do is to plot this data over here, and I've shown the ticket price here as the x-axis and the tickets sold as the y, and it's shown as the dots in this chart. Then I've put a trend line to it, and I can see that a log distribution, log equation, fits pretty well. So I'm going to take that the tickets sold is equal to 117 times the log of the ticket price plus 483, and has an r squared of 0.98. So now let's go get some other parameters for that. Over here I've used the line s function to calculate the parameters for based on those the cumulative number of people who would buy tickets. And this line s function actually returns an array and not just a single number. And so what I've done here is pulled out different elements of that array. Here's a graphic from the Microsoft Help Desk that shows that in the line S function, depending on how many parameters you give it, you get the coefficient b, the first term, second term, third term is going backwards, and the standard errors here. And what we're interested in is the r squared and the standard error, the estimate. So in this result, we'll see the 117 corresponds to 117 over here, and the 483 corresponds to the number over here. I'm interested in this number here, the 4.614. That's the standard error of the y. How can we use that to come up with a confidence interval around our estimate? Well, first of all, we need to calculate how many tickets will be sold by the equation. So over here, I have used the 117 and the 483 to calculate how many tickets would be sold. In this case, it would be 106 tickets sold at $25, 85 tickets sold at $30, and over at $60, it would be 4.2 tickets. So it doesn't match exactly our sample data. But remember, this is a good approximation. We are now going to calculate the confidence interval. So let's start with the P99 upper band. It's calculated as the expected value from the equation times the normal inverse at the P99th percentile times the standard deviation, and then adjusted for the degrees of freedom. So let's use the f of x function to evaluate this. So it's f of x gives us the 106, this 106. The norm gives me 2.32. So 2.32 standard deviations from the equation line gives me the 99th percentile. And then I multiply by the standard deviation, which is the 4.6, and then adjust for the degrees of freedom. And that results in the 119. Similarly, for the P1, it's the same equation, except we've used a minus sign and subtracted the P99. We now plot the confidence bands on our graph. So the P99 is this orange line, and the P1 is the gray line. Now let's stand back and look at it and say, does this make sense? The blue dots represent our raw data, and these are the confidence bands around that, such that if we sold the tickets for $40, we'd expect this kind of a range in here for the number of tickets sold. We are now ready to take the data that we've derived in this initial model, the equations and relationships, and bring them over to our SIPmath model. So over here, I've listed the ticket prices, 25, 30, up to 60. And to the right of this, I've brought in the minimum, most likely, and max values from our equation. So here, the 94.27, 94.27, the 119, the 119, the 106, and the 106, all the way down. This represents the number of tickets that would be sold if we were offering them to a population of 100 people. However, we're going to offer it to more people than that. Let's assume that we're going to offer it to a population of 4,000 people. So these numbers need to be grossed up to the 4,000. So let's go look at, let's say, 40 here, dollars. I'll make this big now. So if I offer the tickets at $40, I'm going to take, let's use our f of x function here. Going to have 5166 divided by 100 times the population of 4,000, and then I've got a max ticket here, evaluate. So what's that max ticket? It represents the maximum occupancy of our building. So it can never be more than 3,900. You'll also notice in this equation I have a max of this proportioned number and 0. Never have negative attendees. So here we've got a 0 even though this is a minus number. So this represents how many tickets would be sold, minimum, maximum, and most likely at these various ticket prices. So let's put a price here of, let's say, $37. So what should be the attendees, the number of tickets we would sell at $37? Well, $37 is between 35 and 40. So what we want to do is interpolate between these two numbers, and these two numbers. I'm going to do that in a transparent way by picking out the appropriate columns here, rows, excuse me, to interpolate between. So we're going to start by finding that row that has the price just below our cost per ticket. So in this case, row 3, 1, 2, 3 has 35, which is just below the 37. And we get that using the match command. Then I'll use that row to pull over the numbers here of 2196, 2692, and 3187. And then just below that I'll put the next row of 1571, 2000, 2562. Now that I have these two numbers, I can use the trend function to interpolate. What the trend function does is take the known y's, the known x's, and the new x's and calculates the associated y value. So in our case, the known y's are these tickets sold. The known x's are the prices, and the new x will be our cost per ticket. So that's what we've put into here. The known y's, known x's, and the cost per ticket. We then also put in a maximum of the max tickets. We've done that for each one of these. We are now ready to do our analysis. And the SIPmath model has already calculated the distribution. And so at $37, my expected value is $63,293. Oh, we ought to come back here and look at one more thing. Look at this graph over here. So we'll notice that our P90 gets chopped off at the 3,900 because of the max tickets. And at the high price tickets, it gets chopped off at 0 because I can't sell negative tickets. Otherwise, we've got a nice confidence band here, and this represents the number of tickets sold relative to a population. Now the question becomes, what is the maximum price that we should pay, or optimum price we should pay, to maximize our profit? So we'll go over to Data, Solver, and we'll just check this real quick like. We're going to D52. We're going to maximize that by changing our cost per ticket, subject to the cost per ticket being less than or equal to 60 and greater than or equal to 25. So we'll solve here. and it has converged, and it tells us that we should be paying $31.85. That generates a profit of $66,093. And I had previously stored that number over here. We didn't capture the number of tickets sold previously, but let's put that in. So that's equal to the revenue divided by the ticket price. So what we see, let's take the $30. At $30 we were selling $37.82, and over here we're selling $34.06 probabilistically. And at $40 we're selling fewer tickets. As a consequence, our profit function is a lot lower with our new market demand than it was with the old. We can see that if we plot the profit as a function of the cost per ticket. Here was our original data, and now here with the survey we've lowered our expectations, and we've also lowered the price of the ticket. Okay, I think we've covered the 3 topics I wanted to in the epilogue. If you have any questions, you can contact me, Brian Putt, through LinkedIn. I suggest that you visit probabilitymanagement.org, where you can review some additional videos and browse through these tabs once again, and then look at the book The Flaw of Averages by Sam Savage. Hope you found these videos of value.